up in the corner over here is your assignment. That is due for Tuesday up there, and some of you already handed it in, and it looks very good. Not today, but you handed it in already last week, Friday. This one is to be handed in on Thursday, but we also have a test on Thursday. And the test is 5.4 through 6.2, and the 6.2 is what I'm really doing today. That part, not the end of the chapter, which I'll try to do some more tomorrow. Okay, here we go. We have this problem, and we're going to go from 0 to pi fourths of the sine of x all over cosine squared x dx. Lucas, u substitution. What am I going to be using u equal?
Oh.
You like it?
Yeah.
Okay, good. Now I'm going to take the derivative of this, and that's going to be du equals what? Okay, got it? Okay. Now, do a few more things while I'm at it. Here's x, here's u. This is going to be from 0 to pi over 2 over 4. When x is 0, what is u? 1. And when x is square root of 2 over, I'm giving you the answer. When the cosine is
square root of 2 over
4, and so I'm going to write it this way instead. You can write it the other way too. But in this case, I think it's going to be a little easier for us, but whatever, both work. Okay, now, my new interval is going to be from 1 to 1 over square root of 2. Square root of 2 over 2, okay? And this here, I need a minus here, so I'll put a minus out here, okay?
Why do you need a minus to make it a positive?
No, I needed to make this a du. Instead of writing du, this here now is exactly like du. Okay, that's here. And this is x, so this is going to be 1 over u squared. And you can see at this point it's a very easy problem. Okay? You have here actually u to the minus 2 and its antiderivative. Do we have a question?
Yes. Don't you leave the minus out front though?
Oh, I forgot. Yep, thank you. This minus is supposed to stay here. I lost it. Okay? Now, the antiderivative of this is u to the... Okay? Why? Because the derivative of this is equal to this.
Oh, okay.
Got it?
Why are we using
Okay? So this is what I'm going to have over here now. And some probably aren't listening very much for this, but you're really going to get nailed harder on the next test than you did in the past one for not giving me a procedure. You can't work these things by not using proper procedure. Okay? So the next step here is going to be 1 over a negative u, and there's a negative out here, like this, and this is going to be evaluated from 1 to 1 over the square root of 2. Any questions about this here? Okay, these two negatives make a positive, so we've got to worry about that.
Where did the negative come from inside the parentheses?
Right here.
Okay.
Okay, good question. Okay, now, put this in, and I get square root of 2, don't I? Put this in here, that's why I did it that way. That's the square root of 2. That's done. And now I have to subtract this one, which is 1, and I'm done. Okay?
Can you explain how you got the 1 over u?
This 1 over u here, from here. Okay, I have this, and I want to find the antiderivative. The way to find the antiderivative of the basic unit is raise it by 1. It was a minus 2, so now it's going to be a minus 1. And then you have to divide by that. Example, if I had this, x to the nth dx, its antiderivative is x to the n plus 1 all over n plus 1 plus a constant. Are you with me? Now, you heard the question asked, and it gets kind of tricky. And you guys haven't seen this kind of stuff before, so those are very normal kinds of questions. Okay? And I just doing a little attendance here just a minute. Okay, yes,
So u to the negative 1 over negative 1.
oh, just a second.
That, so that, no, that's equal to 1 over u.
Yes, because see, this here is in the top, so I put it in the bottom. And then there's a minus 2 there to start with. Yes,
Okay.
yep. And see, that's why I took this form.
Yeah.
Now, otherwise, you're doing it again and just, it can get a little tricky. Okay, any questions on anything else? Okay, now, Lucas and Grant, will you, along with everybody else, go to page,
And just,
to page 378. A very, very nice problem, and it deals with what we've been working with in terms of interpretation of an integral. And you notice in that problem, guys, and others can chip in, that we have this nice little equation like this. And in the business community, I'd like to know what this means. Now, what does he tell me this function is?
Production cost
It's a little bit more than that.
in dollars.
Approximate cost.
Marginal cost. Dollars.
Oh, all of a sudden DeVries used another word. He said marginal cost. Okay? What in the world does that mean?
It means the cost, what you're actually making off the top after.
it's without expenses.
No, that's why I like the wrong answers. Lucas, what do you think? What is marginal cost?
I'm with Grant.
Okay, marginal cost is this. What does it cost you to make the next item?
Oh, yeah.
Marginal cost is always what is it going to cost you to make the next item. See, this is the rate of change in terms of dollars per item. Okay, it's costing you dollars per item. Now, in this kind of thing, what I want to talk about here is not so much the mechanics of the problem, it's what in the world does this mean? And this says he's a book publisher. Okay, what is the cost of making a book here? What is some basic stuff there?
12.
12 minus.
0.0002.
Okay, now, the more you make, it's going to cost you less for making books, right?
Yeah.
Yeah.
Because if this is equal to 1, basically it's costing you $12. But if this is 1,000, this will be considerably less. Why is it costing you less as you make more? Whole bunch of reasons.
Because less is more.
No, that's not one. Okay, you're in the
Because it
business.
lowers the supply or the supply and demand cost.
Okay, your fixed costs that you have built in there. And also, as you make more of them, you probably don't need any extra employees. And your machines, you don't need any extra machines. If you're making 1 or 1,000, so what? You know, you only need that one machine to do it. And also, when you get into higher ones, you probably are going to run a double shift. And there are other kinds of efficiencies. So generally, and this is just a linear one. This is a very, very simple one. Because usually they're curved. Because after you get out there a ways, then all of a sudden it becomes more costly. Because you probably have to go another shift, and that's another interesting math operation. And you might have to buy some more machines. Also, you're working your staff, your employees too hard. Up to a certain point, no big deal, they can work, but they get fatigue sets in and all those other factors. But this is just a nice linear equation, okay? Now, the problem says, what is it going to cost me to go from 12,000, I've been making 12,000, but I want to make 15,000. What is that cost going to be? And this is the change of cost. See? So this is like this, and that's why we got that rate in our interval, minus 0.0002x. And you see this is extremely easy. Okay? Any questions about the manipulation of that? And when you do this, this is going to be the cost of making 12,000 books, and this is the cost of making 15,000 books. Okay? Because when this is done here pretty soon, you're going to get C at 15,000 minus C of 12,000. We'll see a little bit more of that today. Any questions about that kind of stuff? Now, doing business, these are the critical ones. What does the formula look like? And they won't be this simple, I'll guarantee you. Okay? But it's a very nice one for dealing with a business problem. He asks another question at the end. Checkpoint at the bottom. Would the cost of increasing the production from 9,000 to 12,000 books be more or less than the cost of increasing the production in this case?
What? More.
It would be more. Why?
Because your x is smaller, so it's 12 minus a less number.
Here your x is smaller, okay? And over there your x is larger. Well, it's the other way around. Yeah, the other way around, okay? So, that's what I wanted to show you here. And I like the one with cells much better. And sometimes a business model will look a lot like that one too. But I want you to see this one and say, okay, that's what it's dealing with. And now you also have a reintroduction of marginal cost, the cost of making another item. And here, each one is changing, which is also rather significant. Okay, the next thing today. And you're going to find out many of the things we're going to be studying are just built on some of the intuitions that we have. And I'm going to figure out right now, let's see, is this, okay, here. I have these two little functions, trying to make it kind of easy for us. And I would like to know what the area is between these two lines, between here and we'll go over here. Okay? Now, I would like to do it with geometry first, and we can figure out what that is. Now, the idea here, we're doing a simple problem at this point because this is a straight line and that's a straight line. This will probably be the last two straight lines you'll ever see here. Okay? Because we're going to use curved lines. Maybe one of them will be straight, but what we're going to do here is this. Now, so, you notice, what's this length from here to here?
4.
Okay,
2.
from here to here is 4. That's 4 units. 1, 2, 3, 4.
Oh.
Okay, and this point right here is 2 over, so this is 7 up, and what's this and down?
3.
See, now this is the equation here.
-3.
-3. So this side is
10.
10. Did I have that right? Yes, okay, that's 10. And this side, this point is going to be, that's pretty easy to see. You can just see it up there the way I've graphed it.
-7.
And -7. So this side is going to be 22, right? So the area of this trapezoid is going to be 10 plus 22 divided by 2, average, times the height, which is 4. So it's going to be 64 units squared. Okay, now we're going to use the calculus to do this. And this is to teach you how the system works. Okay, I'm first going to take a look at this function here. And I'm going to use f of x and find its area from 2 to 6, like this, dx, which turns out to be nothing more than 2 to 6 of 2x plus 3 dx. Okay, now what is that going to give me? It's going to give me everything from here up to the x-axis. Oopsie. Okay, you see this? That's the area I'm going to get there. Then what I'm going to do is I'm going to subtract from this part here. Now, that in terms of the Riemann sums that are coming out is what? Is that positive or negative? Negative. So I'll just put a negative here, and now it's going to be positive, right? And I'm going to do it this way, a minus x plus 1 dx. Any questions about that? Okay, now what, instead of doing it in two parts, I'm gonna put them all together, yes.
Do you always subtract them, or only if one is
Okay.
all above or opposite?
Listen very carefully. You always subtract the top one from the bottom. Excuse me, you
If
subtract
you're
this one from that one.
If you're under the x-axis.
Yeah.
No matter where you are. These both could be above the x-axis. And I'll show you that in a moment.
When you
Why
get
do you
small,
subtract
remember them? Why wouldn't you just add the,
Okay, at this point, no matter what, it's always going to be, it's always, and this is what I wanted to show you, it's always going to be f minus g. Always. Now, but we're going to tweak that thing, so various things are happening. What is so amazing about calculus, and especially integral calculus, all these things are always taken care of when you're looking at Riemann sums. And I want to show it to you, I'll show it to you in more detail in the next problem. And then we're still not going to be finished. I'll show you it again. And the thing is, we don't have to worry too much about it. You just all of a sudden say, hey, well, I see all that all works. Okay, so these are together. And so now notice, these are going to the same place. So what I'm going to do here is go to 2 to 6. And this becomes 2x plus 3. And this is going to be plus x minus 1. Yes?
Okay, so in the g of x, it's negative x minus 1.
Oh,
And then-
I copied it wrong down here. This is supposed to be a minus, so this is going to be a plus. Okay, now, let me show you something else. At this point, it's only here because we can observe it. Notice at this point, no, I won't go there. I'll just leave it be. Okay? So this turns out to be now, from 2 to 6 of 3x plus 4 dx. What's the antiderivative of that?
X,
Yeah.
3x squared over 2,
Plus,
4x.
and again, oopsie, this is 4x. Make certain that this is back here with a 2 and a 6. And, okay, this is going to be equal to 36 times 3 over 2, right? Plus 24
So that,
minus the quantity 12 over 2, is that right?
yeah,
Plus, because the minus is over here, 8, like that. Okay? Now,
64.
and that's equal to 64. Have you done the calculation? Okay, if you do the calculation, you also get 64. Okay? Now, that's a nice, simple one to take a look at. The trouble with this book is that he gives us such difficult ones to start with. And, yes?
Why is that? Did you just like subtract the one line from the other line to get it all together?
Yeah.
Okay.
Okay, now, this one, I'd like to show you some things. And what I'm going to do here is we have this parabola up here. And what I'd like is the area between these two lines, between this line and this line. This one's on top, this one's on the bottom. Okay? And so it's going to be the blue minus the red. Okay, now let me just show you a few things up here on the board so you can get a little bit of an appreciation of what's happening here. I don't know why this is fogging up here. Okay, now look at what this is. What do I want to do first? Let me just do this one first. This is the red one. And do I have a red marker here? Let's do this. What is this here part, which is x dx? And we're going to run, where are we going to run to? Okay, we've got to find this point and this point because we want the area between these two. And see, next week we're going to rotate it around the axis. That's not very difficult. So we want to find that area. And this point right here is going to be a minus 1, minus 1. And this point here is going to be 2, comma 2. Any questions about that? And you put these two together to solve it. you know how to do that, right?
Yes.
Nothing too miraculous about that? Okay, now, I'm going to be integrating from this point right here to this point right here. Ooh, see that? Now, what is this red one going to give me? Okay, and I'm going to go from a -1 to 2. Okay, now that is going to be net area. I would like everybody to watch here. This way, please. Okay, now this area is going to be, we're doing, okay, so it's going to be, let's see, how do I want it to do? That's going to be these Riemann sums here and these like this here. Ooh, where am I? Like this, like that. See it? With me? Okay. And so I'm taking this one away and I'm adding all these. Are you with me? That's what this does. Okay, now let's take a little bit of a peek at this one. Let's look at this one. And we're going to run it from a -1 to 2, and that's going to be x squared minus 2 dx, like this. Okay, now, that's going to be from the x-axis again, x-axis here, and so it's going to be all of these. Those are all negatives, aren't they? But we're not stopped. We have to go here yet. We're going to put these in too. Are you with me? What have we done?
Why the outside?
Because we're taking it from this point and to the x-axis. Here's our x-axis.
Okay.
And so it's net area. So we have the blue here and the blue up there. Now, notice the part that's doubled. You notice there are certain sections that are doubled. And then, what isn't doubled? This section here is not doubled.
So.
See that?
So what?
So, then we're trying to find that purple. Do we have the purple? If I would do this, if I would, just a second here, this is on top, if I would just now subtract from this x squared minus 2 dx, like this, and get this dx out of here, like that. This one, x minus this one.
Yes.
Okay, because, okay, now, these little red ones here, up and down here, are those positive or negatives?
Negatives.
Those are negatives. What are these crosswise this way?
Those must be positive.
They're positives, why?
To cancel each other out.
Yes, they're because we have this here, see this?
Oh.
I am subtracting those,
Oh.
okay? They're negative too, but a negative makes them a positive. So they're out of here. How about these up here? Okay, these vertical ones out of here are all positive, okay? But these blue ones are positive too, but I'm subtracting them.
So.
They're negative.
Anywhere where the two areas overlap, they subtract one another.
Do you hear that? Yes, automatically. That's what's happening here, okay? Yes.
How do you know which one is on top and which one's on bottom?
Okay. You hear that one? What's on top? This is higher and that's lower. Now sometimes they can crisscross and then we have to do something else, but that's coming later.
Oh.
This line is above this
So
curve
just
here.
within the-
Because this part is not what we're considering.
Okay.
It's starting from this point to this point. If they flip along the way, then you have to take a picture and look, yes.
So could we do one that's all the areas above the x-axis?
I didn't think of doing that this morning. Just a second. Oh, yes, I have one. I have one here. We'll do that one in a moment. See, now this problem is very simple, very, very simple, because you just had, from what I explained, and you don't have to explain it anymore if you understand what's happening with the derivative. And so what we have here is this. We have an integral.
Can you put
Can you
it
put it
down?
back up?
Oh, yes. Yeah, let's see here. Back up here, and this down here. Okay. Now, I'm running from a -1 to 2, and this is on the top, so that's x, and I'm subtracting this one from it. Okay? That's all there's to it.
So now you find the antiderivative and
The
evaluate.
antiderivative,
Okay.
which gives me x squared over 2 minus x cubed over 3 plus 2x, and evaluate it from 1 minus 1 to 2.
Alright.
Okay? And you just crank it out, and there's the answer. I did this one, and I believe I'd like to just stop. It happens to be 2 ninths. Okay? 2 ninths, 9 halves. 9 halves. Dyslexic. Okay? That's how that one works. Okay? Now, that assignment up there deals with some of these kinds of problems. Okay, now, here's another one. In this case, this one will also be probably the first one I do tomorrow, because I'm going to do it again and do it quite differently. And I'm going to do it easier tomorrow than today, although you were going to want today's also. Okay? Now, we got 3 things. We have this line, we have this curve, and this curve. Now, you notice the curve, this is just x cubed. And so at this point, what we're looking at is this line and this line. Okay? So we're really looking at this triangle over here. So what we're going to do then is going to take the derivative, and this point I think is a minus 6, and we're going to run to 0. And this is going to be x plus 6 dx, like that. And then what we're going to do, we're going to go from 0, integral 0 to, this is 2, that's 2, and now we're going to take a look at this curve right here, and this one's on top, okay? That one's on top, which is going to be x minus x cubed dx. See that? This curve here is x cubed, and this is just, oh, just a second, I have something wrong. This isn't right. This is x plus 6, like this, minus x cubed dx. Okay? Yes?
What did you just do?
Oh! You see this section from here to here? See, the first section here is going to be this part right up to here. That one.
Oh, okay.
And this one here is going to be this section right in here.
Okay.
But why, oh, okay.
Okay? And they both happen to be all above.
Why are you subtracting them again? Because they overlap, like that
But
section.
you're adding that?
Okay, now you're having a little trouble here, right, Grant?
Yeah.
Okay.
Within that function, why are you subtracting the x plus 6 minus the x cubed?
I think I do up there. Okay, you notice this part right here. This part right here
Yeah.
is everything all the way up to here. It goes all the way through.
Well,
See, that's everything all the way up to this line. And this here is I'm going to subtract, and what I'm going to subtract is from here to here, from this line to the x-axis. I'm subtracting this part.
So can you put those two together right away?
Oh, yes. Oh, these two, no.
Okay.
But these, you know, that, it doesn't go down.
You can do like -6 to 2.
Nope. They're different areas are different from place to place, so you're stuck. Okay? Now, the big thing here is to show you top to bottom. Tomorrow, we're going to go right to left. And we're going to go up the y-axis. So I highly recommend working through some of these so you have a little idea and appreciation for them. Okay?
So if they crisscross, you have to divide it into sections, so you can do each separately.
What's that again?
If the two lines crisscross, you're gonna have to divide them into sections.
He says if they crisscross, and there's some really nice ones to do that, then you have to, when they go past each other, you have to do it over and divide it into sections. Yes. Okay? Now, there's one other thing I want to teach today, and that's really, I think, just pretty simple, but mainly a visual. Yes?
So for that last one, that deal that you had,
Yep.
for the triangle thing, can you just use geometry to find the area of the triangle?
Okay. No, he said, hey, how about just using geometry this way? I notice this author does that occasionally. Yes, I wouldn't have any problem with that. Okay, this say, hey, that's just a triangle, so you would just do this section.
Are those points, each of those points worth, like, equal to 2 then? Is that why it's 6?
Yeah.
X plus 6, okay.
The ones up.
Okay, now, here's another little calculus one. I want to give you this equation. Y equals the square root of x. And we're not going to do a whole lot with it, but I just wanted to show you something here. This is the function. Now, I'd like you to evaluate this thing from 2 to 4.
Okay.
Okay? Now, again, we're not going to, we could calculate, but we're not going to. Now, to do this, to find this area here, I'm going to go like this, from 2 to 4 of the square root of x dx. And, oh, I think I do need to do what I'm going to do. Let's just do the next part too. This is going to be x to the
3 halves.
3 halves.
2/3.
3 down here, 2 up here, and we're going to go 2 to 4. Okay? Now, this is what I'm trying to teach you at this moment, to help you understand what's happening here. When I put this number in here, in this function, I'm getting all this area. I'm starting from here. First part of the fundamental theorem of the calculus says we go from here to here. This part subtracts us from it. That's always what's happening. Okay? You probably knew that. If you didn't know it, well, now you kind of see what's happening, what this does. This takes you all the way from 0. This gets rid of what you don't want. Okay? Now, let's see. See, now, this problem we just did, I will erase this a little bit tomorrow. This in here. What we're going to do is we can do this a little quicker by doing it in the y-axis and do Riemann sums running this way. Maybe I could also do something with, here, I'm going to do something else here too. I have a couple of minutes, and if there are no other questions, just show you what we really have, because we've just been developing so many things that you probably get a little bit lost. Okay, now, in terms of the calculus of this thing, y equals the square root of x, when I'm trying to figure out these lengths like this all the way through here, all the way down to b over here, here's a, I'm taking all these, and each one of these is going to be delta xy, y, okay? And see, so when you get to your equation here, this thing is actually this dx part. That's what that turns out to be. See, now tomorrow we're going to run these things going the other way, and then these will turn into dy's. And that just does a little trick on the brain, but otherwise it isn't too bad. See, now, and you're going to put all these together as we're going, and it's the distance from, or yeah, the height from the x-axis. This is up, and this is down. And you wanted some that were both up, so I kind of showed that to you. Yes?
So when you say the test is through 6.2a, do you just mean through what we learned today?
Yes. Yes. And, yeah. Again, the first problem won't be on. That's too easy. Okay? Because then Aaron would say, well, I'm going to do it with geometry.
Are there any proofs we're going to have to know?
No. All this stuff, now we're going, is just developing it on the basis of some of the stuff we had.
Okay.
There'll be a little definition. Okay, you're asking about that, and again, I'll share that with you. Top of page 384. And I tried to develop that today for you so it's very intuitive. It's the area of a region between two curves. Suppose f and g are continuous functions, and you notice f is bigger than g. Okay? In other words, f is on the top, g is on the bottom, on the interval a to b.
Yeah.
Then the area is from a to b, and x is on top, and subtract g. Okay? And Greg was talking about what happens if they crisscross. Well, then you have to stop it right there, and then they flip. And if you wanted to see a problem like that, it would be something like this. This equation right here, like that. And that's y equals the cubed root of x, I think. And then I will do something that runs this way. Okay? And we're gonna go from this point to this point. Okay? And at this point, the blue one all of a sudden is on the top here and is on the bottom here. Now, the other thing is, if you'd notice this, you'd say, well, what I'm just gonna do is one-sided symmetric and just double the answer. That is not what I'm trying to teach here. I'm just trying to teach that if you had a function that's not quite as nice as this, you would, wherever they crisscross each other, you have to take that into consideration. Okay? So, can we talk about anything else? Couple people still have to take their test. Be nice if that would get done soon. I don't think it pays to sit down and start working, does it?
No.
Okay.
I gotta get to work.
Well, you've been working all day?
No, but.
Oh, what, you mean work?
Work with some reward.